Hello everyone. I'm going to go over Lab 2 in ENGG 225, and this is on DC resistive circuits. So we're going to be playing around with some interesting circuits, the voltage divider, the current divider, and the Wheatstone bridge. So let's get right into it. So there is some background review, so it's talking a little bit about the theory of the circuits, and we see in the figure the voltage divider circuit, and we know from lecture that we have these relationships. So if we wanted to find the voltage V1 in this circuit, we know that that's going to be equal to V1, or V1 is going to be equal to R1 over R1 plus R2 times Vs. Okay, so that is a proportionality of Vs with the resistor combinations. And what we note on the denominator, it's all of the resistors in series with that voltage source, and in the numerator, it's the resistor of the voltage that we want to find. Okay, so then V2 similarly is going to be R2 over R1 plus R2 times Vs. Okay, so that's the voltage divider. Okay, we have a little typo here, so let's catch that. So this, here, I'll use red, because that's what we use for marking. R1, okay? That's just a little typo, just pointing that out. Okay, and let's keep going. We have, now further down, we have the current divider circuit. Okay, so now the current divider is an interesting circuit. If we have a circuit like this with two parallel resistors, then for the currents we have this relationship. Oh, I'll use blue again. So I1 is equal to R2 over R1 plus R2 times Is, and we see that there's some relationship or similarity with the voltage divider, except now we notice that the resistor that goes on top is the other resistor. Okay, see, the R2 resistor is associated with the I2 current, whereas we're solving for the I1 current and we use the R2 resistor. Okay, so don't get caught by that. Okay, so then for I2, we use the other resistor, so it's R1 plus R2 times Is. Okay, so now this only works, let's just make a note, only for two parallel resistors. Okay, so those equations only work when you have two parallel resistors. And further down, we show a very interesting equation. So that's this one right here. And this is a general equation for the current divider. So if you have a whole bunch of parallel resistors, you can find the current in any individual one by using the conductances. So remember, conductance is 1 over R, right? It's a reciprocal of resistance. So then what we have is the conductance of the resistor in that branch that we're interested in, what the current is associated with the current of that branch. Okay, so that's very interesting. So if we were to go up here, if we were to use a conductance formula, then what would we be doing? We'd have, let's say, I1 is equal to G1 over G1 plus G2 times Is. Okay, let's just make sure I did that right, make sure there's a correspondence. Okay, so there's a correspondence between those two. So that would be a way of using conductances, and the formula kind of makes more intuitive sense like it does for the voltage divider. Okay? Okay, so then we get into the Wheatstone bridge. So all of this that you see, all these equations for the current divider and the voltage divider, are just explaining some of the theory of where things come from. Okay, so now we have the Wheatstone bridge. So this is a very interesting circuit, a very powerful circuit and widely used for instrumentation. And the basic idea is that if we were to get a voltmeter, so let's say Vm for voltmeter, so that's a voltmeter, and if we were to measure the voltage across A and B, we would actually be able to determine the resistance. So then let's see what that would look like. So now we see a plus and a minus in a VAB measurement, okay? So what that actually means is that the black lead is going to come around and connect to B, okay? So this is the black lead. And then the red lead is going to come around and connect to A, okay? That's the positive, okay? So this is the red lead, okay? So that's how you would hook up your voltmeter to make a measurement VAB, like so. Okay, and now what you're going to derive the equation for this, but by measuring VAB, you're going to be able to figure out what that resistor value is, okay? So then, let's get into the lab, okay? So there are pre-lab exercises. So what you're going to do is you're going to design the voltage divider. So what are the important things about this one? Okay, so this voltage divider, you're required to produce the voltages of 12 volts, 7 volts, and 2 volts, okay? And that is from a source voltage of 15 volts, okay? So this point here is going to be 12 volts. This point here is going to be 7 volts. And this point here is going to be 2 volts. And that is all with reference to the reference node, which is 0 volts, okay? So now, what else are you required to do? So the other constraint to this design project of yours is that the total resistance is going to consume 500 milliwatts of power. So that's half a watt, okay? So then you're going to have to design this. So now, how are you going to do this? So you're going to use resistors in the lab, and these are the resistor values that are available to you, okay? So 100 ohms, 390 ohms. My table got a little messed up, so sorry for spilling it over on you like this. Let's make it look a little nicer, and it's probably not helping, but there we go. Anyway, you get the idea. So you have from 100 ohms to 100 kiloohms. Those are the values that you have available in your lab handout. That's what we have in the lab. So from those resistors, you're going to construct the resistors that you need. So now what's going to happen? So let's see what that circuit can look like here. So let's just go here. Okay, I'm just going to draw it out for you. So now, let's say your circuit is going to look like this. So like here's the 15 volt source. So that's 15 volts. And then you're going to come around and you're going to see this R1. Okay, there's a correspondence there, right? And out here, this node is going to be 12 volts. And coming down, you're going to have the R2 resistor. But now, you have to make that R2 resistor out of the resistors that you have available, and it has to comply with the calculations you've made to get the 12 volts, the 7 volts, and the 2 volts from that voltage divider, and all of them together dissipating 500 milliwatts, okay? So now that R2 resistor could be, you know, a series parallel combination of resistors, right? You might have to put a couple of resistors in parallel. Let me just make that a little bit nicer for you, okay? It could be a series parallel combination of resistors to get the right resistor value, right? So you could be doing that, and all of that could be R2. So let's just say, let's say in red, all of these can be R2, okay? And then this point here will be the 7 volts, okay? So this is 7 volts. And then you can have another similar structure, and I don't know if it's going to be a structure like this, okay? You're going to have to calculate it and figure it out. You're the engineer, you're the designer, okay? It could be something like this, a series parallel combination, and then over here could be the 2 volts. And so this set of resistors, it could just be one resistor, I don't know. You're going to have to be the one that designs it, and that could be the R3 resistor. And then at the very bottom here, we'll have that final resistor that you're going to have to design. And it could look like this. Who knows, maybe there's going to be 3 parallel resistors, if that's what makes sense in your circuit, right? Okay. And this is the last resistor, and that's the one that's going to come around and go back to the negative. Okay? So then that last one is going to be, what do we call it? The R4 resistor. Okay? Now each of those, you know, you don't know. Maybe this is just one resistor. Or maybe it's 2 parallel resistors, whatever it is. So this is a design project. Now how do you go about doing this? Well, you can get out your calculator and start randomly punching numbers and deriving series parallel circuits or whatnot. That's one way of doing it. Another way is maybe getting an Excel spreadsheet and putting in the formulas for series and parallel, and then you could just put different numbers in and it'll automatically calculate for you. That could be one way, a little bit better than punching everything by hand in a calculator over and over until you get the right values. And another way, and I'd like you to think about this, is use the tools in your toolkit. Last semester you took ENGG 233, so you learned how to program. And what you can do is you can write a program to explore this design space and come up with a solution for you, okay? So if you're interested in doing that, maybe we can have a conversation. I could give you some ideas and you can go ahead and program it. You have the set of possible resistors. You can put in the resistor structures that you want to explore, series parallel combinations, and then you can just get your program to do the work for you and find the resistor combinations that meet the requirements of the project, okay? So let's keep going. That's the voltage divider part that you're going to design. So then you're going to design the current divider. So what's happening there? So these are the requirements for the current divider. You need to have a circuit that produces branch currents of 16.67 milliamps, 10 milliamps, and 6.7 milliamps. And you're going to implement the circuit with a 15 volt source in series with a 100 ohm resistor, and the total current going in has got to be 33 milliamps, okay? So let's just take a look down here. So the total current going in is described here. So this is 33.3 milliamps going in, so that's going into the circuit, okay? And then each branch current is like so, 16.67 milliamps, 10 milliamps, and 6.7 milliamps, okay? So you have to design the resistors or specify the resistors R1, R2, and R3 that meet those requirements, okay? And you may have to use series and parallel combinations to come up with each of R1, R2, and R3. Okay. The last thing you're going to be doing is analyzing the Wheatstone bridge. So you're going to construct a Wheatstone bridge circuit, okay, and this is going to be really interesting. So what you're going to have to do is come up with a value of R3 to balance this Wheatstone bridge. So basically the ratios of the resistors have to make sense. So this resistor here, this is going to be a thermistor, and at 75 or at 25 degrees Celsius, it is going to be 75 ohms. So knowing that that's 75 ohms, you need to specify R3, the value of R3, so that that Wheatstone bridge is balanced. And if you recall from lecture, a balanced Wheatstone bridge is when VAB, so VAB is here, right? VAB is here. It's a voltage difference between A and B, points nodes A and B, and that's when it's 0, when VAB is equal to 0, okay? So balanced means, balanced means VAB is equal to 0 volts, okay? And you'll notice that the Wheatstone bridge is 2 voltage dividers, one on the left side with node A and one on the right side with node B. So you can come up with a way to analyze this, okay? So then let's keep going. Okay, so now here's a tricky part here. Okay, so let me see, one sec. So this is a tricky part. So what you're going to have to do is come up with an equation, right, that looks like this. So right here, you have to obtain an expression for VAB in terms of RTH. What does that mean? So what we want is you're going to come up with VAB is equal to some expression, right? So it's going to have a bunch of terms there and there if it's like some sort of fraction. And then within it, within the right hand side, there's going to be an RTH term in there, okay? As part of the circuit analysis, okay? And remember, keep this in mind, remember that VAB is equal to VA minus VB. And you can use a voltage divider to calculate VA and another voltage divider to calculate VB, and then combine those together by just going VA minus VB, and VA minus VB is VAB. Okay? So then, once you get that expression, then what you're going to do is rearrange the expression to express RTH in terms of VAB. So you rearrange this equation. So then let's say rearrange to get in the form of RTH is equal to some expression, whatever, there's going to be maybe a numerator and a denominator, and inside of there is going to be a VAB. So then why do you want to do this? Like, what's the point? So the point is that when you're using this circuit, using this circuit, let me get rid of the stuff in the way here. So when you're using this circuit, you are going to put a voltmeter. So voltmeter, you are going to put a voltmeter in the circuit with the black lead coming over here to B and the red lead coming over here to A, and you're going to make a voltage measurement, right? And that voltage measurement is going to be VAB. Okay, so then you're going to plunk in the measured, so you're going to measure VAB, and then you're going to plunk it into that equation, and your equation is going to tell you RTH. So what's the point of that? So Now, this RTH is a thermistor. So this is a thermistor, okay? This disc. And what it is, it's a device that's sensitive to changes in temperature, and it changes its resistance. So when we measure VAB, we measure its resistance, okay? And so, like when we, and when we know the resistance, we can know the temperature. Okay, and then how do we know the temperature? This is the tricky part. Okay, I'm gonna jump down into here. So now we are using a thermistor whose operation is defined by this graph that you see here. So this is a graph that's a little bit difficult to interpret. Now, this graph shows many different lines, so these lines that are sloping up towards the right, those are for different thermistors, and our thermistor is 1. So our thermistor is 1, okay? And that is this line right here. So that's the line that we're going to use, the 1 line, okay? So not 2, but 1, okay? So so that's this line right here, okay? 1, okay? So now, how do we use this? Well, we're going to calculate our resistance, okay? And then we're going to go on to the logarithmic scale, and we're going to say, okay, like let's say we got 75, right? So let's say 75 is like right about here, okay? And then we're going to come across, let's say 75 ohms, and then we're going to come across, let's say wherever, over here, and we're going to hit this line right here. Okay, perfect. Okay, so we're hitting 1, okay? And then we're going to drop down, we're going to drop, and we're going to come here, okay? So then, what's that point, okay? Well, we have to interpret this, so right over here is 3.3, and right over here is 3.35. So let's say that that's 3.35, okay? So now, what do we do with that information? So now, look, there's 2 scales here, right? There's one scale over here, and that's where we got our 3.35. But then we have another scale down here, okay? And that's in temperature in Celsius. But we see that the yellow scale is a non-linear scale. So this is for humans to read, so to get a rough idea. So if we were to drop down that red line all the way down, we'd get 25 degrees, okay? And that's what we're going to expect. At 25 degrees, that thermistor has a resistance of 75 ohms, like what we discussed earlier when we were talking about balancing the Wheatstone bridge. So now, so let's say 25 degrees Celsius, okay? So now, but the orange scale is a lot more precise, okay? So if we want to make a proper measurement, we'll use the orange scale, and I'm going to show you how to use the orange scale. So now, let's see what the units are. So the units for the orange scale are here. So I'll just highlight this part. So it's the reciprocal of Kelvin and times 10 to the minus 3, okay? So that's what the units of the horizontal scale is. So if we want to convert that to Celsius, what we do is this, and I'll just use, I'll use this side here. So let's just say temperature in Celsius. Celsius is equal to 1 over the horizontal scale. So that's going to be the 3.35 times 1,000, and then minus 2. Oh, sorry, I'll just do the minus here. Minus 273.15, which you'll recognize as the offset for Kelvin. Okay, so let's calculate what we have here with our like we pretend we've measured 75 ohms, right? So then the number that we got when we dropped down is 3.35, okay, times 1000 minus 273.15, and that works out to, what is it, 25.35 Celsius, okay? So if I were to measure 75 ohms with my voltage measurement and my calculation, I'll get 25 degrees as a result. Okay, so now let's take a look at how to construct these circuits, okay? Okay, what I've got here now is a breadboard that's showing you how to connect the circuits. So let's just step through these one by one. And the idea for this, why I'm showing you this, is so that you can see how to build the circuit. So let's just go really quickly to the voltage divider. Okay, now what I've got here for you is the breadboarded circuits that you're going to build, and I want to show you how to build these circuits in a way that makes sense. So let's go to our voltage divider circuit, and it's really good to build your circuit in a way that looks like the circuit in your diagram. So right here, I'm just going to cover this up with paper so that you don't get confused by the other circuits. We can see that there's a correspondence between these two circuits, or this circuit and the voltage divider, okay? You see how we have the source on the left hand side, the 15 volts, the R1 resistor horizontal, so that's over here, okay? And then we have the 3 resistors coming down, so that's these resistors here, okay? And then we can make measurements across these resistors to check the values, okay? So that's how we build the voltage divider circuit in a way that looks like the circuit in the diagram, and it's going to help our debugging quite a lot. Okay, let's take a look at how we may build our current divider circuit. So now we have our current divider circuit here, okay, on the bottom. We have our red and white going out to where the 15 volt supply is going to be. So that's this guy on the left here in yellow. And then we have a 100 ohm resistor going up, so that's a 100 ohm resistor. And then we have 3 resistors in parallel. And we've put them across like this, 1, 2, 3. And we've got jumpers going across, showing the parallel connections up here. And the reason why we've built it this way is that we're going to come across and measure the currents. So let's say we want to measure the total current. We could take this jumper out and measure the total current going across something like this, okay? So we can selectively take out the jumper wires and measure the current. So we could take out this jumper wire and so forth, okay, and make a current measurement. So we have the 3 resistors going across like that. Okay, so that's a way of building the current divider circuit in a way that looks like the circuit diagram, and it's much easier to see it working this way on the board. Okay, and then for the Wheatstone bridge, we have a circuit like this. So we'll have our plus or minus 15 going to the top and bottom of the Wheatstone bridge like so. We have the resistors in a diamond shape, and then we can get our meter and make a measurement like so. And then we can measure VAB across like that. Okay, so we can make our measurement there. And this is our thermistor. So one of the things we're going to do with our thermistor measurement is we're going to we'll first measure it in ambient temperature and see if we can estimate what the temperature is of the lab. And then we're going to pinch it with our fingers, and it should get hotter, of course, because we're warmer than room temperature. And then you can make a measurement of that by measuring VAB, and then calculating the resistance, and then using the graph to find the temperature. And then what we're going to do is we're going to use some cold spray. So that's going to be super cool. And what this does is it shoots out a liquid which evaporates really quickly, so we'll just blast it for a very short time, just like what I did there, and then that'll bring the temperature down, and then we can measure the temperature of what it went down to. And so it sprays a liquid which then evaporates, and that's what makes the thermistor cold. And then another test that we're going to do is we're going to use a hairdryer, and we're going to use the low setting on the hairdryer, and then apply heat to the thermistor, and then see what temperature we can read. So that's the lab. There is the pre-lab component, okay? So make sure that you do the pre-lab and be ready to complete the lab and make the measurements and record the measurements during the lab. Okay, good luck with the lab. It's a fun one.